new chapter today. And in this chapter, we're going to really start to begin to look at real versus imaginary numbers. We mentioned them in chapter 1. We talked about our number sets. We said how the real numbers can be rational or irrational. Even rational numbers have subsets of them. We had our integers. We had our whole numbers. We had our counting numbers. And now, we're going to see another branch of numbers in this chapter called the imaginary number set. And we're going to actually see today where an answer becomes imaginary. We're not going to get to it just yet, but we're going to talk about how it works. Okay, and we're going to discuss this concept of I. So, let's start the beginning first, okay? We'll take a look. So, the square root was invented to solve the following equation. That was the reason. If I had something that said x squared equals a number, that's where the square root came from. If I have a number times itself equaling something, I have to solve. And there's two answers to that equation, denoted as radical b and negative radical b. Radical b and negative radical b. Now, if you don't believe me, we're going to look at an example in a moment to prove that. But where have you seen that before? Like, what's the square root of 64? Or, why is it negative 8 also? What's the reasoning behind that?
When you square it, it will become positive.
Yeah. When you square negative 8, it becomes positive. Good. All right. So what's the cube root? The cube root of 8.
2 or negative 2? Just 2.
It's 2. Because it's a cube. So if it's negative 8, what's the cube root of negative 8? Then it's negative 2. So with squares, when you take a square root, you have to take a square root of a positive number. If you take the square root of a negative number, that's where imaginary numbers come from, actually. We'll talk about that today. But when it's a cube, okay, when it's a cube, all you're looking at is either the positive or the negative root, depending upon what you started with. But with a square, it's plus or minus. So let's look at some examples to start, and you'll see this. So the first one, radical 4, we know is simply 2 or negative 2. Now, there's something that we're going to talk about in this section where if you're just reducing, all you need to write down is the positive root. Okay? It's called the principal square root. The principal square root. Let's jot that down. When you take the square root of a number, all you need to write down is the positive root. When you solve an equation, though, that involves the square root, you have to take both. Again, if you're just evaluating a number like radical 4, the answer is just simply 2. But if you had something that said x squared equals 4, then the answer is 2 or negative 2. How about part B? How about part B? It should be pretty quick, right? Part B. What is the value of negative radical 16? Or it should be really stated as the opposite of radical 16, which is? Yeah. So the square root of 16 is 4, but the negative is on the outside, so we have to tack on that negative. Okay? We have to tack on the negative. This should be, like, very common sense. How about part C? Part C is another easy one. Morgan? 3/5. So that clearly tells me that if I have the square root of a fraction, I can take the square root of the top and the square root of the bottom separately. Agreed? Okay, root 9 on top. Root 25 on the bottom gives me 3/5. So again, we are giving answers for what are called the principal square root. All right. Let's see examples. So similar to what we just did. Part A. Part A. We have x squared equals 25. So I want to solve it.
Plus or minus 5.
Plus or minus 5. Now, why do I need both answers? Here's why. Set this equal to 0. Watch what you do. If you think about this. Subtract 25. That's what you get, right? What's x squared minus 25, really? Factor. Not 0, no. I said factor x squared minus 25. What does it become? Yeah, that's why you have two answers, guys. Easy way to remember. You're going to get x equals negative 5, x equals positive 5. You're going to get both of those. Okay, negative 5 and positive 5. So if you forget that when you're solving an equation, you need to get both answers, just move it over and factor, and you'll see that you get both answers. But you don't need to do that step if you didn't want to. You could go right to the answer from part A, right here. You can jump right to the answer. You do not need to show setting equal to 0 and factoring. Part B? Part B? It's already set equal to 0. Positive and negative 7. So that means that this factors into, right, that means that this factors into x plus 7, x minus 7, if that's true. But that's a plus sign. It's not a minus sign. Remember, difference of squares right here, Will, factors into this. There's no such thing as sum of squares, unfortunately. Now, what I want to do here is think about it this way. Move the 49 over. Because it can't be factored, unfortunately, part B. Can you think of a number, when squared, that gives you negative 49? Can you think of a number, when squared, that gives you negative 49? I'm thinking about a nose. You're right. Be confident. You're all right. You can't. This is where imaginary numbers are going to come from. For now, just write no real solution. In section, I think like 6.4 or 5, we introduce imaginary numbers. Okay, for now, though, there's no real solution. No real solution. Whenever something squared is equal to a negative number, or something to the 4th power, or the 6th power, or any even power, equals a negative number, the answer will be imaginary. And we will talk about what that means and how to use that. Okay, but for now, just write no real solution. Part C. I can do part C several ways. What do you got?
Is it root 5?
It's root 5, but it's also
Negative root 5?
It's also negative root 5. So I can do this two ways. I could factor out a 4 to start, which makes this, right? Then I could go ahead and say, all right, well, this technically, believe it or not, you could think of this as difference of two squares. It's not, though. This is kind of weird, so stay with me. Right? If this number were 16, what would it factor into? If this number were 16, what would it factor into?
X plus 1.
Yeah, you take the square root of the 16, right? So this is a 5 now. So take the square root of 5, which is just square root 5. So believe it or not, this does factor into x plus root 5 and x minus root 5. And I know we haven't done that yet, because I've always hounded you guys that it has to be a perfect square. Well, 5 is, in my mind right now, a perfect square of radical 5. Okay, so you can write it this way and you get two answers. Or you could just solve the equation. So we're going to get this as an answer. We're going to get this as an answer. Okay, in blue though, watch what I'm going to do at the bottom in blue. In blue, I'll just solve this. Move the 20 over. Divide by 4. Which gives you plus or minus root 5. Okay, either way works. So move the 20 over, divide by the 4, square root both sides, remembering the plus or minus. Yes?
I did it.
How'd you do it?
I just took the root of 4x squared, and I got
2x.
You get root of 20, which you can then turn into 2 root 5, right? And then you just divide by 2.
Yeah, that works good. Yep, so you recognize this as like difference of squares, but the 20 became root 20. Yep, because remember the 4x squared becomes 2x, right, when you square root it. So the 2 that you take out of the 2 root 5 ends up canceling. Good, nice to know, Nico. You can do that well. So again, many ways, clearly, right, to solve these problems. But the idea here is to remember that when you solve, write yourself a little note, when you solve an equation involving a square root, you get two answers. Whenever you solve an equation involving a square root, you get two answers. Plus or minus here, plus or minus here. And you're always going to get two answers. Even later, when the answers are not real, the middle one, part B, the imaginary answers we're going to see how to do, you'll still get two answers. Okay, you'll still get two answers there. So that was a square root. How does a cube root differ from the square root? Because students really fumble on cube roots in notes in the last few years. So I want to make sure we understand it first. How does a cube root differ from a square root? Or a fourth root? Or a fifth root? What does it mean? Let's start by asking this question first then. start by asking this question. A cube root looks like this, right? Agreed? A fourth root looks like this. So, what's the deal with a square root? Why does it just look like this? What does the 3 and the 4 indicate? What do the 3 and the 4 indicate?
The power is being multiplied by.
Okay, the power of whatever you're reducing. So what should really be here, Morgan?
2.
A 2. A square root, believe it or not, has a 2 there. You just don't write it. It's always been there. This 2 is indicating find a number when multiplied by itself twice that gives you that answer. So when you have a cube root, it's saying find a number when multiplied by itself 3 times you get that answer. A fourth root. So the fourth root of 16 I know is 2. Because 2 times 2 times 2 times 2, 4 times, gives me 16. The fourth root of 81 is 3. 3 times 3 times 3 times 3 is 81. The third root, or the cube root, of 27 is 3. Because 3 times 3 times 3 cube root gives me 27. So when you see a fourth root or a cube root, think, can I put a number here 3 times so that it gives me the answer I had? Can I put a number here 4 times so it gives me the answer I have? In a square root, we know it's 2 times. You're looking for that number. Okay, that's really what's physically happening with a cube and a fourth and a fifth root. So let's take a look at that now. Okay, we're going to see clearly that it's to solve this equation. Okay, cube root is a solution to the equation x cubed equals b. Now, when you take a cube root, though, you don't have a plus or minus as the answer, because your answer for a cube root could be positive or it could be negative in the inside. And let's prove that so we can see it physically. So, the first one we did already, unfortunately. I gave that as an example. But the cube root of 27, you need to think to yourself, what number cubed gives me 27? If no number cubed gives you 27, you might have to break up that number into different components. And we'll see more of that in the next and later sections. But I think of this as, so the cube root of 3 times 3 times 3 is just 3. Okay, that's how I think about it. What 3 numbers, when multiplied, the same number, obviously, when multiplied 3 times, gives me what's under the radical? Well, 3 is, so the answer happens to be 3. You take whatever number goes in this blank here, whatever this number is, here, here, or here, same number, and that's the number that comes down. How about part B? Part B, Morgan? Negative 2. And clearly Morgan knows that it's negative 2, because negative 2 times negative 2 gets me to positive 4, but another negative 2 gets me back to negative 8. Okay, it's negative 2, negative 2, negative 2 gives me negative 8. So the answer is indeed negative 2. C. Part C. What thing times itself gives me 10 to the 6th if I multiply it 3 times? What times what will give me 10 to the 6th? 10 to the 2nd. 10 squared, 10 squared, 10 squared is how many 10s? 6 of them. So think of this as the cube root of 10 squared, 10 squared, 10 squared. So as a result, if I take a cube root of a cube, it's just simply 10 squared, or 100. Part D. Part D. Nico? D to the 4th. Cube root of d to the 4th, d to the 4th, d to the 4th. Doesn't that give you d to the 12th? 4 and 4 is 12. So the answer is d to the 4th. What conclusion can we draw from parts C and D? What conclusion can we draw from parts C and D?
I don't really know how to word it, but the number that's under the radical sign is divided by the negative on that side.
Very good. So let's talk about our terms then. Okay, I haven't gone over these terms. I didn't realize that. I'm thinking I assume you know these. So the exponent, Emily says, take the exponent of the radicand and divide it by what's called the index. So let's write these terms out, please. I'll put it down on the bottom here. Okay, so n is the index. A is the radicand. And then this symbol here is called a radical. Okay? Those are your three terms. So for part C and D, when you have variables involved, because we're going to have variables involved, when you do have variables involved, we take the variable's exponent and divide it by the index to get our answer. Now, that's assuming that they're evenly divisible. If not, we'll see what we have to do. Okay, we're going to have to break it up if we have to do that. Oh, no wonder why I didn't define this. It's on the next slide. About that is on the next slide. So, in this, we can generalize and say the nth root, where n is what? Where n is any number. So the second root is really the square root. The third root is really the cube root. And then after that, you don't say anything. You say fourth root, fifth root, sixth root, etc. Okay? You don't say like quadruple root or something like that. Okay? It doesn't. You don't have to use those numbers. But square root and cube root are common terminology. So this is the solution to the general equation x to the n equals b. So if I had something like this, I know it's not going to work. Okay? I know it's not. Let's say I had this. There's no answer to this numerically, but if you were to write it out, it would be this. Make sense? Whatever the exponent is that you're trying to get rid of, you take that nth root. So if I have x to the 6th, I take the 6th root. And when I take the 6th root of x to the 6th on the left-hand side here, right? Look, I take the 6th root of that. The 6th root of the 6th power cancels, which is what makes the answer just simply this. Okay, again, a root and its exponent will always cancel it to the same. If I have the 6th root, I take the 6th power, I take the 6th root. If I have the 12th power, I take the 12th root. Something you should write down, and we're going to go over it at some point this year, but it's good to know in this section. A root is the same thing as a power, but with the exponent as the reciprocal. So for example, this could be written as 12 to the 1/6 power. Again, if you want to take a 6th root, you can just do 12 to the 1/6. Whatever the index is, becomes the denominator of this rational exponent topic it's called. We'll talk about rational exponents at a point this year. Okay, but this denominator of a 6 comes from the index itself. So in your calculator, you can type 12 caret parentheses 1 divided by 6 close parentheses to get the answer to this. Because there is no 6th root function on your calculator. It doesn't exist. Okay, there's a square root. There is a cube root function also. But once you get above square root, say you need the 10th root of something, type in that number to the 1/10th power. If I need the 15th root, that number to the 1/15th power. But the power needs to be in parentheses if you're going to raise it. Okay? That make sense? All right, let's look at the next example. Part A. Step me through it, please. Don't just give me the answer. What are you thinking when you see part A? What's your first thought? What do you have to do?
Well, I think of the cube root of 8.
Okay. You thought of the cube root of 8.
If you were to multiply that by 2 again, then it would be 16.
So he thinks of 2 because 2 cubed is 8. Another 2 gives him 16. Very good. Why did you do it another time? Why did you go to a 4th? Why not cube?
Because it's asking for a 4.
Yeah, it's asking for a 4th root. So Inigo said, well, these 3 give me 8 if I multiply them, so he's missing a 2 over here. So negative 2, negative 2, negative 2, negative 2. But what's the problem? It'd be positive 16, wouldn't it? So is there any real answer for this one? There's no real answer for this one. There's an imaginary answer we're going to talk about, but there's no real answer. So let's write a quick statement before we go on to part B. What statement can that be? Give me some sort of a corollary or conclusion of some sort.
Even roots. Negative numbers rooted by even number,
Okay, I'm
will
with you.
have no real answer.
Yeah. Now, an even root of a negative number does not exist. No real answer exists, I should say. Okay? For an even root of a negative number, you will get no real solution. Okay? No real solution. So, we shouldn't have a problem with part. Ooh, that's fast. What you can do, guys, listen. What you can do, the next two you can try. C should be easy now that we came up with the corollary family. Just take a look at the video for number 5, please. We can go over it, but you don't need to be able to do this. So look at the video for number 5. That's all you have to do. Okay, your homework is there. Okay, do your homework over the weekend, please. Yes.